Calculus often gets this bad rap for being this long, scary list of rules you just have to memorize. But what if that's the wrong way to look at it? What if, and stick with me here, you could have actually invented it yourself? Well, in this explainer, that's exactly what we're going to do. We're going to build it from the ground up just by tackling one simple-looking problem.
Okay, we've all had this formula drilled into our heads since, what, middle school? Area of a circle is pi r squared. But have you ever stopped to ask, why? I mean, really, why? How would you prove that's true if you had to start from scratch? This isn't just a geometry pop quiz. Thinking really hard about this one question is our secret door into the biggest ideas in all of calculus.
Yeah, just by wrestling with this one familiar shape, we are literally going to stumble upon the core concepts of calculus, integrals, derivatives, and the absolutely profound link that ties them together. Our whole story starts right here, with a plain old circle and a single, really clever idea.
All right, so where do we even begin? Well, a great first step in any math problem is to respect the object you're working with. A circle has this beautiful symmetry, right? So instead of just chopping it up randomly, let's slice it into a bunch of thin, nested, concentric rings. Like the rings inside a tree trunk. That feels elegant. It feels like a really promising way to start.
So the game plan is pretty straightforward. If we can figure out the area of each individual ring, one by one, then we can just add all those little areas up to get the total area of the circle. Makes sense, right? So let's put one of these rings under the microscope and see what we've got.
So let's just grab one of these rings at some random radius we'll call r. Now, imagine you take a tiny pair of scissors, you snip it open, and you unroll it. You lay it out flat. What does it look like? Well, it's not a perfect rectangle, but it's pretty darn close, isn't it? And the great news is, we definitely know how to find the area of a rectangle. That's something we can work with.
Let's look at the dimensions of our new sort of rectangle. The length of it, its width, well, that's just how long the ring was before we cut it, which is its circumference. And we know that formula, 2 pi r. Okay, what about its thickness? Well, that's just the tiny, tiny distance from one ring to the next. Let's give that tiny change in the radius a special name. We'll call it dr.
In this little dr thing, that's the secret sauce. That's the whole key right here. It represents the thickness of our slices. And here's the crucial insight. While our rectangle is just an approximation, it gets better and better the thinner we slice our rings. As that dr gets smaller and smaller and smaller, our approximation gets closer and closer to being perfect.
So the area of any one of our rings is roughly its length, 2 pi r, times its tiny thickness, dr. Now for the big step, we need to add up the areas of all the rings, from that tiny little dot at the very center all the way out to the circle's edge. And how we choose to visualize this sum, well, that's where the magic really happens.
So our total area is going to be the sum of all these little rectangular areas for every possible radius from the center to the outside. Now I know what you're thinking. That sounds like a monstrously complicated addition problem with like thousands of tiny little pieces. Who has time for that? But wait, what if we stopped thinking about this as a long list of numbers to add up, and instead, what if we arrange these pieces into a picture? This one shift in perspective is about to crack the whole problem wide open.
Check this out. This is so cool. We take all of our unrolled rectangles and we just line them up side by side in order from the smallest one at the center to the biggest one at the edge. And what shape do they make? Would you look at that? Their heights trace out a perfectly straight line, and all together they fill a perfect triangle.
All of a sudden, finding the area of the circle is as simple as finding the area of this triangle. The base of the triangle is just the circle's full radius, r, and its height? That's the circumference of the biggest outermost ring, which is 2 pi r. And the area of a triangle is 1/2 base times height, which simplifies to pi r squared. There it is. We just did it. We derived one of the most famous formulas in all of math, right from scratch.
Okay, that insight was incredible. But a real mathematician doesn't just solve one problem, they build a tool that can solve lots of problems. Our big trick was turning a complicated sum into finding the area under a graph. We just got lucky that our graph was a nice, simple straight line that made a triangle. So what happens if the graph isn't a straight line?
Let's really level up and ask a harder question. What's the area underneath a parabola, the curve y equals x squared? Now, all of a sudden, our little triangle trick is out the window. This is a totally different animal. It's going to require a new way of thinking. Okay, first things first. Let's just give this thing we're looking for a name.
We'll call it a of x. It's some mystery function that will tell us the total area under the curve from the starting point up to any endpoint x we choose. This area function has a special name in calculus. It's called the integral. And for right now, it is a complete mystery.
You know, when you're faced with a really hard problem, sometimes the best strategy is to just play with it, poke it a little, and see what happens. So instead of trying to figure out the whole function a of x at once, let's just see what happens when we nudge its input just a tiny, tiny bit.
So if we increase x by a tiny little amount, let's call this one dx, then the area is going to grow by a tiny little sliver. We can call that sliver dA. And what's the area of that new sliver? Hey, it's another one of those skinny rectangles. Its height is simply the height of the curve at that point, which is x squared, and its width is just our tiny nudge dx.
And this is where we find a stunning relationship. That tiny change in area, dA, is approximately equal to x squared times dx. Now watch this. If we do a little bit of algebra and just divide both sides by dx, we find that the ratio of the change in area to the change in x is just the height of our original function.
This ratio, dA over dx, this is the other huge idea in calculus. It's called the derivative. And a derivative is just a very precise way of measuring a rate of change. It tells you exactly how sensitive a function is to tiny little nudges of its input. This isn't just for finding areas. It's how you calculate the instantaneous velocity of a rocket, or model the moment-to-moment changes in the stock market. For us, it tells us exactly how fast our area function is growing at any given point.
And this is the moment. This is where everything just clicks into place. We started with what seemed like two completely separate ideas. The integral, which was all about finding a total accumulated area, and the derivative, which was all about finding an instantaneous rate of change. And now we're about to see they are not separate at all. In fact, they are two sides of the exact same coin.
What we just discovered is the whole ballgame. The derivative of our mystery area function, a of x, is simply x squared, the function we started with. This means that finding a derivative and finding an integral, they're inverse operations. They are opposites. They perfectly undo each other.
This incredible relationship, the idea that the rate of change of the area under a curve is the curve itself, is the single most important idea in all of calculus. It's got a name that's as big as the idea. It's called the fundamental theorem of calculus, and it's what connects these two giant concepts into one beautiful, insanely powerful theory.
So just think about that journey. We started by simply slicing up a circle, and we ended with one of the most powerful tools in all of human history. Because at its heart, that's what calculus is. It's a method for taking a problem that seems impossibly complex and breaking it down into an infinite number of beautifully simple pieces. So I'll leave you with this question. What complex problem in your world would you want to solve first?